Hi you guys, this is Carol, and this is my mini lecture on chemistry in case you feel like you need a little more background if you haven't had chemistry in a while or you haven't had it at all. So when we look at the periodic table of elements, you're going to see boxes like this one that are referring, this is the nomenclature for the different elements. And as a definition, an element is a substance that cannot be broken down by chemical means into other substances without a whole lot of energy, because now we can actually blast it in a lab and do it. But this is without all that energy input. So in this box here, then we have the name of it, Fe, which is iron, and these two numbers, 26 and 55.847. So you want to know what those are. And these are slides that are from your text, so I want you to be looking at your text. An element's atomic number, so the number up at the top for oxygen here, 8, indicates how many protons are in each atom of that element. And the protons are the positive particles. For a class like this one, we're not that concerned with the protons and the neutrons. We're more concerned with electrons and what they're doing. Okay? So let's move on and think about those electrons. Electrons are the negative particles, and they are found in these shells surrounding the nucleus that has those protons. So if protons are positive and electrons are negative, there's going to be an attractive force there. And we draw them like this with these orbitals, but in reality, we don't really know exactly where they are. They're somewhere in that vicinity. So it's easy for us to draw them like this to be able to visualize it. An important concept when we're talking about bonding of atoms is what the valence shells are doing, how many electrons are in the valence shell. So here are two examples, and one of them is copper and one of them is gold, and they may have more or fewer shells, and with greater or fewer numbers of electrons. But what matters to us is the outermost shell. That is the valence shell. For copper, this one, and for gold, this outer one, both of them actually end up having one electron in that outer shell. So as a definition you have here in chemistry and atomic physics, an electron shell or a principal energy level may be thought of as an orbit, followed by electrons around an atom's nucleus. Okay, so this is an example of carbon. It has 6 protons, 6 neutrons, and 6 electrons that are circling around that nucleus. This is water. Very important. We have a whole section on water. And the water molecule here is shown in 4 different ways. With more detail, where we could see the electrons, to the least amount of details, where all we have is the O for oxygen and the 2 H's for hydrogen. Sometimes we can show it with dots, showing the number of electrons, or ball and stick, or coming here with the total number of electrons. So, in the outer shell, the first shell fills with 2, and then beyond that, it's going to go to a different energy level. So this second energy level here fills with 8. So look at oxygen. In that outer shell, the valence shell, it has 1, 2, 3, 4, 5, 6, making it unstable. 8 will make it stable. So in this molecule, you're seeing these shared electrons. Hydrogen has 1, and in that first shell, it is filled with 2, and it only has 1. So it could do with some sharing. It could share 1 and end up with 2 in its vicinity. This hydrogen only had 1. It could end up with 2 in its vicinity if it shared. And oxygen, by sharing these extra electrons, would have 1, 2, 3, 4, 5, 6, 7, and 8. That makes it a stable molecule, a non-reactive molecule. So that is the shape of water. This is another example of shared electrons, oxygen in the valence shell. In this oxygen on the right, let's say we see it in green, it would have 1, 2, 3, 4, 5, 6 electrons. It needs 8. If it's up close to another oxygen molecule that also has 6, it could do with sharing 2 electrons. Sharing 2 electrons means it has a double bond. 2 electrons are shared. And now when I count the vicinity here, I have 8. And if I count this vicinity here, it has 8 in that outer shell. So it becomes stable. This is oxygen molecule. Here you breathe. The description is here again. In chemistry and atomic physics, an electron shell or a principal energy level may be thought of as an orbit, followed by electrons around an atom's nucleus. Okay, defines it well. These 3 examples I posted for you there. Filling the first shell with 2, 1 extra, very reactive. Filling the first shell with 2, 8 in the second one, not reactive. 2 in the first, 8 in the second, and 1 more in the third. 1 here, very reactive. It wants 8. It wants 7 more. Okay, those are just examples of lithium, neon, and sodium. So valence shells are the farthest from the nucleus, and that's what matters for bonding. Your text that I'm referring you to has a nice way of talking about that you're going to be reading. It shows the electron with a ball filled in and a vacancy with it empty. So there you can see, okay, I want 8 in carbon. I only have 4. I have 4 electrons and 4 vacancies. Okay, so that's a nice way of thinking of it. Very helpful. This allows you to see valence shell fills with 2, 8, and 8. Where are the vacancies? So in oxygen, we have 2 vacancies. Nitrogen has 3 vacancies. Carbon has 4 vacancies. And hydrogen has 1 because that first orbital, that shell fills with 2. And that's where I want to stop with this mini lecture. Okay? See you soon.